Hello, everyone. My name is Runzhou, and today I will talk about our research on building quantum virtual machines. This is joint work with Hongzheng Zhu, Jason Nieh, Jianan Yao, and Ronghui Gu. And quantum computer is coming into reality, and now there are multiple cloud platforms like IBM, Amazon, and Microsoft that provide on-demand access to real quantum hardware. And researchers are using those quantum cloud platforms heavily and running trillions of circuits. However, the usage model of quantum computers on the cloud right now is very naive. Even if you are running a very small quantum program, let's say this small quantum program with 2 qubits on a very big quantum computer that have hundreds or more than thousands of qubits, you still get the exclusive access to the entire machine that no other people can use them, even if you only use a very tiny fraction of the computer. It's like very backwards and like how people use mainframe classical computers in the 1960s. And this naive usage model leads to massive underutilizations for the cloud platform providers, and it means very long delays for the users. Usually hours or occasionally users will wait for days for their job to run on the quantum cloud platform. Therefore, it is very urgent to improve the utilizations of this cloud-based quantum computing platform. And when we look back into the history of classical computing, we can see that we solved this similar problem decades ago very well by using virtualization technique to multiplex computation resources. And for decades of development, we now have a very rich ecosystem of virtual machine technologies. And the wisdom behind virtualization is decouple the virtualized world and the physical world. It decouples the user's view of the machine from the physical reality. It allows users to compile their programs once just to the virtualized machine backend. And in the real life, in the physical world, there is a hypervisor makes some smart and dynamic decisions at runtime about how to schedule and place those multiple jobs on the real hardware. And our goal is to bring this same philosophy to the quantum world. However, building a quantum virtual machine is not easy due to the unique hardware properties of quantum computers. First, there is a hardware topology constraint about quantum computers. Here is the topology graph of IBM's 127-qubit Eagle machine. And each node denotes 1 qubit, similar to classical registers in the CPU. And each edge means a link between those 2 qubits that enable the operations across these 2 qubits. Unlike classical CPU, that you can basically access any register or doing operation across any different memory, in quantum computers, you can only do interaction or instruction between 2 connected qubits. But what is good about quantum is that instead of like a CPU that you execute instructions sequentially, for different qubits, the instruction on them can execute parallel. This hardware topology constraint leads to a very complicated stage to allocate memory for quantum programs onto the real quantum hardware. It usually involves some complicated graph algorithm to satisfy those topology graphical constraints. And when we come to multiplexing quantum hardware, it becomes an even harder graph problem to map multiple quantum programs onto the real quantum hardware. And secondly, the quantum hardware is in its very early stage, and there is no those advanced features that our system builders like RAM or privilege level control or MMU. This means that we need to build our quantum virtual machine system on a very primitive machine, like with the bare metal structure. So in this work, we present HyperQ, a runtime management system, or we call it hypervisor for cloud-based quantum computing. It contains mainly two parts. One is a quantum virtual machine, or QVM abstraction. We call it a QVM because it has the same interface as a standalone machine, and people can use their existing quantum compilers to compile their program to the virtualized quantum machine backend seamlessly. And we also have a runtime scheduler to schedule those compiled quantum programs and multiplex the real quantum computers. So how can we enable this design of quantum virtual machines? And our observation is that though the quantum computer have those kind of graphical topology constraint, the quantum computer's topology are not some arbitrary graph. Usually it's have some kind of recurring patterns or repeating structure in the hardware. For example, this IBM's Eagle quantum computer have this kind of I-shaped repeating structure and in grids. Then this inspired us to use this kind of repeating structure as the basic unit of a quantum virtual machine. And what's good about this is that this kind of virtual machine abstraction perfectly captures the repeating structure in the hardware. And it means that if you compile a program onto a virtualized quantum machine, it doesn't need any extra computation cost, or you don't need to resolve a graph problem to map it onto the real machine. You just select a grid position and just put your compiled program onto that position. And we want to have virtual machines isolation property. Even if we don't have any like hardware feature for kind of access control, we can utilize the natural topology of the real quantum machine, that between two I-shaped units, there are some other qubits between them. We use these qubits, we basically left them unchanged so that qubits belongs to different QVM regions does not directly interact, and therefore the noise from one side does not propagate to the other side. And we can have small programs and also have larger programs. And for larger program, we provide something called multiplied QVM that takes a rectangle shape of multiple basic QVM units. And user can pick the multiplied QVM for appropriate size according to the program, the quantum program they want to run. So using this quantum virtual machine interface from a user's perspective, the user just runs their standard compilation process onto this kind of smaller machine from a user perspective with this I-shaped hardware topology constraint. And the result will be something we call compiled executables of the original programs. And of course, if the program can compile to different size of executables that characterized by the number of basic virtual machine units that it occupies. Then it comes to scheduling all those kind of, from the cloud provider side to schedule all these different shapes of quantum programs, compiled quantum executables from multiple users on the cloud machine. So the cloud provider will basically just collect all these kind of executables from different users into a job queue. And because we are capturing these kind of repeating structures in the hardware topology, we just now in the scheduling, we just run a scheduling algorithm as simple as just packing boxes or packing chocolates. And we basically use a greedy first in, first out algorithm to pack all those kind of executables like chocolates onto a grid-like machine. And that is very fast instead of originally you need to compute a very complicated graph problem. And we can notice that there's, in addition to space multiplexing, different quantum programs have different like time estimations. So it means that some programs take a longer time to run and some programs take less time to run. And we also run another round of scheduling called time scheduling so that we append another quantum programs, for example, like this, the D programs, to the end of some shorter programs previously scheduled in the space scheduling. And once we combine all the different quantum executables, we now call the cloud platform's quantum hardware to really execute these programs, and we retrieve the results. So now we talk about the evaluation of our performance. We evaluate our framework using two different types of job workloads. One is all small programs, a job queue of all small programs. Every of them is less than 10 qubits and usually fit into one or two basic QVM cells. The other is a medium benchmark that have those kind of small, part of them are small compute programs, and part of them are larger, what we call medium-sized programs that takes up to 27 qubits. We have two different types of arrival orders. One is dense, where all hundreds of jobs arrive at once, and you want to maximize the utilization. The other is a sparse arrival model that every second on average, there will be one job arrive, and we want to evaluate their latency. And we run this for different settings. and we compare our framework to a single thread execution on the IBM's cloud platform. And we can see that about throughput or utilization-wise, we have like a drastic improvement. On the small benchmark, we can have like 9 times improvement on throughput. And on a medium size, we can have like 4 times throughput improvement. And for the sparse arrival model, we still have like more than 3 times speed up on about the utilization. And we also measure the latency of each job. Basically means that how long does it take from submitting the job to getting the result of the job. And we can see that on our sparse model, we can have like 26 times speed up about the latency. And we can find some interesting observation that the compile time using HyperQ is smaller than compile time to the IBM's platform. That is because our compilation is compiling to a smaller virtual backend instead of compiling to a larger graph, the 100-qubit graph of the bare metal machine. And you can see that the running time, average running time on the IBM cloud platform is actually is smaller than the average running time on HyperQ. That is because we are running multiple jobs in parallel. And because of the current limit of the quantum machine, we cannot, if some jobs end early, we cannot retrieve the result until all the jobs running simultaneously ended. So that is why we have a slightly larger running time compared to running each program one by one. So in conclusion, we introduced HyperQ, the first system to introduce virtualization technique to quantum computers. It provides a virtualized quantum machine abstractions and have a scheduler that improves the resource utilization, throughput, and lower the latency. In the future, we are going to explore the quantum virtual machine system with more advanced hardware feature when more advanced feature of quantum computer arrive. And we are also digging into a virtualization across different architecture from different cloud quantum computing vendors. Thanks for listening. And you can check our code online on GitHub. And also I'm hiring research assistant, PhD student, or postdoc working on quantum operating systems.